Predicting patient trajectories is one of the most critical frontiers in modern healthcare. Early detection of sepsis, accurate forecasting of disease progression, and personalized treatment planning all depend on our ability to model how patients change over time, not just in snapshots, but as continuous, evolving processes. And yet clinical time series data, drawn from electronic health records, registries, and ICU monitors, are notoriously messy. Measurements are irregular. Some values are missing. Noise is everywhere. And the underlying biology, it's inherently stochastic. One patient might respond dramatically to a drug, another might barely react. This variability isn't noise, it's signal. So how do we build models that can handle all of this? Today, we dive into a powerful new framework, generative modeling of clinical time series via latent stochastic differential equations, a method that treats clinical data not as discrete points, but as partial observations of an underlying continuous, uncertain dynamical system. Let's break it down. The problem: why traditional models fall short. Most traditional time series models, like ARIMA, assume regular sampling and deterministic behavior. They struggle with missing data, irregular intervals, and the complex, nonlinear interactions that define real patient trajectories. Deep learning models like LSTMs and GRUs improved things. They learned representations from high-dimensional EHR sequences, outperforming older statistical methods. But they're still fundamentally discrete. They process data at fixed time steps, which breaks down when measurements arrive at unpredictable times. Even Neural ODEs, which model hidden states as continuous trajectories, are deterministic. They predict a single path. But in reality, patient outcomes are uncertain. A treatment might stabilize someone today, or it might not. That uncertainty needs to be modeled, not ignored. And that's where stochastic differential equations, or SDEs, come in. Enter latent stochastic differential equations. At its core, this framework views clinical time series as noisy, partial observations of an unobserved, continuous latent process, a hidden state that evolves over time under the influence of treatments, baseline traits, and intrinsic randomness. We model this latent evolution using a neural stochastic differential equation, a continuous time dynamical system where the future state depends not only on current conditions, but also on random fluctuations. Mathematically, this is expressed as dxt mu theta xt ut dt plus sigma theta xt ut dwt. Here xt is the latent state, the true unobserved physiological condition. Is the drift term a neural network that captures the deterministic component, how the system evolves under treatment and baseline covariates? Is the diffusion term another neural network that models the stochastic component, the inherent randomness in biological processes? And dwt is a Wiener process representing Brownian motion, the source of uncertainty. This formulation is powerful because it naturally handles irregular sampling, missing data, stochasticity in disease progression, measurement noise, patient-specific variability. But here's the catch: we can't observe xt directly. We only see noisy, partial measurements, like heart rate, tumor volume, or ECOG scores. So how do we learn this model? The solution: variational inference with Girsanov's theorem. We use a variational encoder-decoder architecture, a probabilistic autoencoder where the generative model is a latent SDE. The encoder maps observed data and treatments into a latent representation. The decoder projects the latent trajectory back into the observable space. But the real innovation lies in how we perform inference. The true posterior, the probability distribution over latent paths given the data, is intractable. So we approximate it using variational inference. Specifically, we define an augmented SDE that conditions the drift on the observed data. This augmented process acts as our variational posterior. Crucially, we use Girsanov's theorem to compute the Kullback-Leibler divergence between the generative and approximate posterior paths, a tractable quantity that allows us to train the model efficiently. This leads to an evidence lower bound, ELBO. Log p y v greater or equal to e dkl, q0 p0 dkl q tau p tau. The first term ensures the model reconstructs the data well. The second regularizes the initial latent state. The third penalizes divergence between the full posterior and prior trajectories. And because we're working with SDEs, we can sample multiple trajectories from the generative model, each representing a plausible future path, giving us not just a prediction, but a distribution over possible outcomes. This is uncertainty quantification in action. Why this matters: real-world validation. To test this framework, the authors evaluated it on two complementary datasets. One, a synthetic PKPD model of lung cancer, a controlled, known ground truth simulation of tumor growth, immune response, and patient health under chemotherapy and radiotherapy. Two, real ICU data from 12,000 patients, physiological signals like heart rate, blood pressure, and temperature, collected irregularly across multiple hospitals. They compared their latent SDE model against two baselines. Latent ODE, a deterministic continuous time model. Latent LSTM, a standard discrete time recurrent model. Results where the SDE shines. On the synthetic dataset, the latent SDE outperformed both baselines across all metrics, especially in uncertainty quantification. Let's look at the key numbers. Predictive entropy, PE, Lower is better. The SDE had significantly lower PE, meaning more confident and accurate predictions. CRPS, continuous rank probability score. The SDE achieved the lowest values, indicating better calibrated uncertainty estimates. NLL, negative log likelihood. The SDE's predictions were more likely under the true data distribution. But the real test came under realistic stress conditions. When they introduced high process noise, sigma equals 0.5, the SDE maintained stable performance while the ODE and LSTM degraded sharply. 80% missing data, the SDE again outperformed both baselines, especially in capturing unobserved tumor volume, where it achieved 20% lower RMSE than the LSTM. Why? Because the diffusion term explicitly models stochasticity. It doesn't just learn patterns, it learns variability. It knows that two patients with the same treatment might have different responses, and it reflects that in its predictions. In contrast, the deterministic ODE produces a single trajectory, no uncertainty. The LSTM, despite being probabilistic in its latent space, suffers from posterior collapse and vanishing gradients, causing uncertainty to decay over time. Real-world impact, ICU forecasting. Now on the real-world ICU data, 12,000 patients, 48 hours of vital signs, irregular sampling, and missing values. The model predicted heart rate, blood pressure, and body temperature for the next 24 hours. Results were clear. The latent SDE delivered more accurate point predictions and better calibrated uncertainty estimates, especially for heart rate and temperature. For mean arterial pressure, all models performed similarly, likely because it's tightly regulated in ICUs. But for the more variable signals, the SDE's stochasticity became a critical advantage. Figure 3 in the paper shows a sample patient. The model captures the general trend, but more importantly, it shows 95% confidence intervals around its predictions, a visual representation of uncertainty. That's not just a forecast, it's a risk-aware forecast. Clinicians can now ask, is this heart rate spike due to noise, or is it a sign of impending sepsis? With calibrated uncertainty, they can answer that question with confidence. Why this framework is a game changer. This isn't just a better model, it's a paradigm shift in how we think about clinical prediction. It's continuous time, so it handles irregular sampling naturally, no need for interpolation or resampling. It's stochastic, so it captures biological variability and provides uncertainty estimates, essential for risk-aware decision-making. It's generative, so it can simulate counterfactuals. What if we had given a different dose? What if treatment had started earlier? It's probabilistic, so it supports Bayesian inference, interpretability, and integration with domain knowledge. Future work could go even further, integrating expert-designed ODEs, combining imaging, genomics, and EHR data, or using the model for real-time treatment optimization via reinforcement learning. Imagine a system that doesn't just predict the next heart rate, but suggests the next intervention with a confidence score based on thousands of simulated patient trajectories. That's the promise of latent SDEs. Final thoughts. In healthcare, uncertainty is not a bug, it's a feature. Every patient is different. Every response is variable. And every decision carries risk. Traditional models treat uncertainty as a limitation to be minimized. But this framework treats it as information, a core part of the signal. By modeling clinical time series as latent stochastic processes, we move beyond point estimates. We move toward predictive systems that are not just accurate, but trustworthy. And in a field where lives depend on decisions, that trust is everything. So whether you're a researcher, a clinician, or a data scientist, this is the future of clinical modeling. Not just prediction, not just automation, but uncertainty-aware, continuous time, patient-centric intelligence. That's the power of latent stochastic differential equations. And that's how we build better, safer, smarter healthcare, one stochastic trajectory at a time.